We left the response we got on Dr. Matej's last episode with us, and since many of you wanted another episode with him, here we are. This episode answers questions on tachyons, time as a physical dimension, and the future of theoretical physics. Dr. Matej has been kind enough to recommend a book for all of us young physics enthusiasts, and it's called Beyond Peaceful Coexistence, and it's based on the emergence of space, time, and quantum. The book holds chapters written by various distinguished physicists, and each of them explains what they are working on and how they are using those concepts to make out a theory. I think you should check the book out, and I'll send the Discord community link in the description, and you should be able to find the book's PDF over there. Anyway, without any further ado, or facing the fourth dimension, let's dive right into it. Talking about things that are traveling faster than light. So, matter cannot travel faster than light, but because it is the universal limit for the maximum speed. But then, can tachyons travel slower than light in any instance?
Oh, yeah. So this is interesting. Look, okay, now first I will share just this video, the screen. Fine. So this is just animation for the beginning. Then I will ask your question. So I will continue with answering your question.
Okay.
And okay, yeah. In the usual 4D, four-dimensional relativity, there is the speed limit, namely the speed of light in vacuum, beyond which an object cannot be accelerated. A slower than light particle, baradion, cannot become a tachyon and vice versa. It cannot be accelerated across the light barrier. A tachyon cannot become baradion, at least not within a classical non-quantum theory. This does not mean that tachyons cannot exist. The theory of relativity can be extended to incorporate slower and faster than light particles. They are related to each other by superluminal transformations. Uh, However, if we consider the speed of light in a material medium, so if we consider the speed of light in a material medium, then a baradion can travel faster than the speed of light in this medium, and slower than light in vacuum. Okay, here I have an illustration of Cherenkov radiation. This is the radiation that is emitted by an object that travels faster than the speed of waves in that medium. Here the medium is water and waves are waves on the surface of the water. You have Cherenkov radiation, and this is this cone, because the boat is faster than the speed of waves. The similarly is if a charged particle travels through a medium, whatever medium in which it can emit light. And then you have this Cherenkov radiation. Now, analogously, according to the extended relativity, a tachyon can travel slower than light in a tachyonic medium. Now we have a tachyonic medium, and we have a tachyon with speed v, and traveling slower than the speed of light in this medium, and faster than speed of light in vacuum, because it is tachyon, is faster than light. Yeah, and then it emits Cherenkov radiation, analogously as the baradion emits. So important is to have a medium, either bradyonic medium or tachyonic medium, and there is complete symmetry between two situations. A subluminar observer will see here tachyonic medium and vice versa. A tachyonic observer, for the tachyonic observer, this will be a tachyonic medium. There is complete relativity. Now, as bradyons do not emit Cherenkov radiation, so Cherenkov radiation in vacuum, so also tachyons cannot emit Cherenkov radiation in vacuum. But usually physicists think that tachyons emit Cherenkov radiation, even if traveling in vacuum. But this is not a prediction of extended relativity, which is based on the principle of relativity.
So you mentioned that only charged particles when moving faster
Yeah,
than
charge.
light. Yeah.
Yeah.
So would tachyons be charged particles if they exist?
Yeah, tachyons in principle can also be charged. Yeah, as usual, particles are charged. The charged tachyons will emit Cherenkov radiation if traveling in tachyonic medium.
Okay. So you mentioned extended relativity while explaining this. So could you elaborate on the basic ideas of extended relativity?
Yeah, look, okay. In the usual relativity, one introduces the concept of four distance, which is an extension of the usual distance in three dimensions. As the usual distance does not change under rotations, so also the four distance does not change. It remains the same in another Lorentz frame. Now, this holds for the usual Lorentz transformations, connecting the reference frames with slower than light speed. So let me show here. Yeah. In extended relativity, the relative speed can be either slower or faster than light. It is if it is slower, then, as I said, the distance in space-time does not change. The s prime squared is the same as s squared. So it means this longer expression for the distance with prime quantities is the same as here. And so the transformation is then this one. For instance, if the object moves in the x direction, then this transformation x and t change into the prime x prime and t prime, whilst the transverse coordinates y and z remain the same. Okay. Now, so here is an illustration of the transformation of the coordinate grid. So this is grid. Each vertical line represents a possible world line of an observer at rest in this system. But here, under Lorentz transformation, these lines become inclinated. And what is interesting, that Lorentz transformation preserve the speed of light, so also the x coordinate must be inclinated, and the speed is is x divided by t. And look here, for the speed of light, if you divide this by this, you obtain the same number as if you divide this by this. You get 1. We use units in which the speed of light is 1. So just for simplified expression, and that's the reason that I put here what I put v, not v over c squared, which is usual in textbook. So yeah, this is just simplification. In theoretical physics, we use simplified units, so to have simpler expressions. Now, if the relative speed is faster, then the forward distance changes. It changes. So we have this expression. And the transformation, the superluminal transformations are this one. Now, you see, if we wish to have this satisfied for y and z, then y prime must be I times y and z, I times z. So they must become imaginary. What does it? So what does it mean? It means that the signature of the metric is no longer plus, minus, 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 but becomes minus, plus, plus, plus. Okay, at this point, let me say the following. Initially, initially physicists considered imaginary time, so that the distance was written in terms of imaginary time. Instead of ECT, they wrote X. For fourth coordinates, they said fourth coordinates is time, but it is imaginary. But then they started to use, instead of imaginary time, they changed the metric. Then they said that the metric for the time component is negative. Metric means what are the factors in front of these squares here. So negative. Now, modern convention is the opposite. In modern convention, we say that the metric along the time-like direction is plus and negative along the space-like direction. So we are now using the metric plus, minus, minus, minus. So minus sign means space-like and plus sign time-like. In the modern, most physicists, most textbooks use this convention. Now, thus, under the superluminal transformations, we have this change of the metric here, as I said, from 1, 3 to 3, 1. So 1 means how many pluses are in the expression for the metric. So this suggests that instead of 4-dimensional space, we must consider 6-dimensional space-time with signature plus, 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 minus, 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 which under a superluminal transformation changes into tuck, 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 tuck. So 3 pluses and 3 minuses, and the opposite under transformation. So 3, 3 plus 3, 3, of course, because there are the same number of pluses under the transformation as minuses. So this is now projection of 6-dimensional space-time into 3-dimensional time part, time-like subspace, and here into the 3-dimensional subspace, space-like subspace. So here this is, yeah. Now, yeah, okay, if you can, if it is clear, okay. Otherwise, if you have something else to ask about Tachyons.
I understood that part, yeah.
Okay, very nice.
So moving on more about tachyons. So what about causality, right? Tachyons supposedly violate causality. So sorry, causality.
Yeah, this is the very big problem for many people. Yes, because with tachyons, one can make arrangements such that a particle can travel into the past. This would make it possible to send a signal into the past. Usage of such so-called tachyonic anti-telephone would cause problems with causality. The problem, so-called causality paradoxes, occur in the naive setup with a classical theory in 4-dimensional space-time. If we consider quantum theory and its many words interpretation, such problems do not occur because the world splits into 2 alternative histories, as for instance in this scenario. So this is a picture from my book, The Stumbling Box. I will not go into details. Everybody can stop the video and read what is written here. I just mentioned here that here are 2 possible branches of the history. In this branch, there was tachyon signal was sent into the past, and here the world splits into two possible branches. In one, there was tachyon was sent into the past, and in another branch, the tachyon was not sent into the past. Because here at this point, one must consider the superposition of two possibilities, and the world splits into two branches. A similar resolution of causality problems with time travel was proposed by David Deutsch in a very known paper that was published in Physical Review D, I think that in 91. So he considered time travel, but it is applicable also to tachyons.
Okay.
Yeah, and similarly, also in six-dimensional space-time, there is no paradoxes of causality. But then, even if you have classical theory, because then somehow, even within classical setup, we can arrange deviations of trajectory, this multidimensional time into different direction and thus into different possibility. Yeah.
Right. Okay, so assuming the problem of causality does not arrive, for which we would have to live in 16 or 6th dimensional Clifford spacetime, would it be possible for tachyons to exist?
I think that yes, extended relativity, in six-dimensional space time or 16-dimensional Clifford space predicts the existence of tachyons. This is prediction of the theory. And so discovery of tachyons would be a crucial experiment that would boost the advance of theoretical physics in many ways, as explained in my book, Stumbling Blocks Against Unification. So I think, according to my understanding, the tachyons should be possible. But this is not so according to the understanding of many physicists, because they are right to see the problems. But maybe later I will touch some of additional problem with tachyons. Yeah, okay.
Okay. So you mentioned how time can have various dimensions, right?
Yeah.
So let's say time is multidimensional and an observer moves sideways in time, where let's say like there is the length, right? The length is past, present, and the future, and an observer moves, let's say, sideways. So would the observer say the same present but different possibilities of the present? If not, what would the observer notice?
Yeah, it depends on how it will move. I will say later more precisely, but now let me say the following. Even if time is multidimensional, usually an observer would normally experience a linear sequential passage of time. This means that his world line would be one-dimensional. His present would change from this hour to next hour, from today to next day, just ordinary passage of time with different layers of present moments. What he would see would depend on the direction of his motion in the multidimensional time. If I move slightly differently, then perhaps I will not go to the trip tomorrow, but I will stay at home and so on. But this would still be, according to me, just a normal passage of time, normal sequence of possibilities. But okay, let me first illustrate the situation in the usual relativity, in which time is one-dimensional. So what we have in usual relativity? In usual relativity, we have four-dimensional space time. I depicted here three coordinates, time coordinates, and two spatial coordinates. Now, the present is given by this surface. Here is two-dimensional, but actually it is three-dimensional surface. On this three-dimensional surface, there are moments of now that we experience now. Okay, there is a problem because we experience in light cone, but in our immediate surrounding, we see three-dimensional surface because the speed of light is very fast. Okay, but what then happens? This surface moves in space-time, and when it moves, here you have a word line in space-time, and if this surface moves, the point, the cross-section of the word line with this three space lies on different position on this surface sigma. Simultaneously surface or spatial hypersurface. This is 3D now. And it, as I said, it moves in the forward direction. And when it moves, it fills the space-time. In the usual relativity, space-time is block space, and this movement of simultaneity is in fact considered as illusion. Yeah. Okay. So let me now. So what happens if time is multidimensional? Then a possible scenario is that the three-dimensional hypersurface sigma moves in the higher dimensional space and describes a four-dimensional surface. So we have now multidimensional space. So now the coordinates are denoted with xi, and these are either space-like or time-like coordinates. Doesn't depend. Okay, as I depicted this surface here, this must be a time-like, and this must be space-like direction. Okay,
Yeah.
so we have this simultaneously surface sigma, which moves, and when it moves, it sweeps four-dimensional spaces embedded into this higher dimensional space. Let, for instance, a six-dimensional space with three times. Okay.
Okay.
So the observer now lives on that surface, and all his word lines is on this surface. This is word line of the observer at rest on this space. So let me see. Yeah, the history is flexible because the sigma surface can move in various directions. So the history depends on how the three surface moves in the embedding space. But there exist alternative three surfaces tracing alternative histories. Now you have alternative history, different space-time, not the one experienced by the observer moving along this history here.
Okay.
Yeah. So this is if the observer. Okay, now your question. If the observer moves sideways through time, then he moves from one space-time to another space-time. So this would be sideways motion. I said that it depends on how, because of course, in any case, the observer moves in this space. But if it moves into time-like direction, then it traces just his usual space-time. But if he moves into space-like direction, then he can move from one space-time to another and experience come from one possible history to different history.
Okay.
Yeah. Look, it is interesting that a scenario with such sideways motion is described in the novel by Kate Laumer, The Other Side of Time. Here it is very vividly, it describes interesting story about this travel sideways in time. I don't know if you encountered this book, but it's very, very inspiring. Yeah. Because it is just like Everett many words iteration would suggest.
I
And
also got this idea from a book actually. It's called Into the Sideways World by Ross Welford.
yes,
Yeah. So there's this girl, she moves sideways into time and she gets into an alternate reality.
yeah. This is a favorite subject of science fiction
Hmm.
novels, but which are nevertheless based on some physics. In this case, on many words, interpretation of quantum mechanics. Yeah, okay.
So following up on the previous question, what do you propose we would see if time is three-dimensional and the observer moves in the z direction of time, like in the third direction of the time?
We would see nothing special. The observer would move along the x direction. So this is observer. Movement means that his borderline is inclined, and it means that it will move in this direction. But if his borderline is inclined in this direction, he will move sideways. So if it moves in the x direction, he will see nothing special.
Okay. Okay. So our everyday experience of time is linear, right? So does your exploration of higher dimensional space times change how you view the concept of time?
In relativity, time is a coordinate besides the three spatial coordinates. A passage of time is not an ingredient of relativity. Look, we have this sigma surface. Motion of sigma surface represents passage of time. So in relativity, we have a block universe. Everything is fixed. Passage of time was considered as illusion. Okay, but what is illusion? Illusion is related to consciousness. The time experienced by consciousness is different from the time as one of the space-time coordinates. There is a lot of activity in physics community. Physicists consider two distinct concepts of time. One associated with our subjective perception of passage of time, and the other is the time of the block universe. But look, normally we perceive time as linear passage. We perceive linear passage of time associated with progression of the simultaneity surface sigma. In quantum theory, instead of a definite sigma, we have different possible sigmas. There is a wave packet of sigma. I discussed something about that in previous podcasts.
Hmm.
But upon wave function collapse, we perceived definite sigma and a definite distribution of matter on that sigma. Such a process continues from collapse to collapse. And at each moment, we perceive a different present, a different sigma. So consciousness moves forward along time-like direction, and so we perceive a linear passage of time.
Right.
Uh, but this is not the case when we dream or meditate or are under influence of drug. Then our consciousness is somehow dissolved. It is not. We are not tracing definite history. We are completely confused. Mm, I don't know if you know the story when the very good friend of Einstein, Bessel, died.
Mhm.
Einstein said, "Oh, don't worry, he just passed a little ahead of me. We physicists know that time is illusion, and that actually everything is written once and for all in the book," something like that. I am paraphrasing
Okay.
something. But of course, according to quantum mechanics, it is not everything written, and in this multidimensional is written even less. So there can be possibility of explanation of dreams and influence under drugs in this setup. But this is subject that is not yet incorporated into current physics and even not current science.
Right. Okay. Uh, Moving on, your early work on brain worlds had paved the way for further research. Can you describe the core concepts of a brain world scenario and how it changes the traditional view of space-time?
What I described is in fact a brain world. I was considering about four-dimensional space-time. This is like a brain. So our space-time is a four-dimensional membrane, a brain embedded in higher dimensions. Later, specific models were considered by several physicists in which the fields of the standard model, I mean electromagnetic and other gauge fields, are confined to the brain, while gravity propagates in the bulk. That is the bulk. This is the name for the embedding space. So those models emerge from string theory, and they differ from my model in specific details. So more about how I look at brain world can be found in my book. Yeah.
Okay. Your research also incorporates Clifford algebras. So, can you explain in layman's terms how Clifford algebras offer a new mathematical framework for studying physics?
Uh, Look, it would make me too much time. It would be very difficult. So it is explained in my book, The Landscape of Theoretical Physics. Something was already said in the previous podcast where I talked about Clifford space as a space of oriented r-dimensional volumes, areas associated with extended object. Here, let me only say that Clifford numbers are, are a generalization of complex number. As two-dimensional space can be described by a complex number, so a Clifford number can describe a four-dimensional space. So here we have complex number, a plus I times b. I is imaginary unit, and this is a Clifford number. And this E1 and E2 are generators of Clifford algebra in two-dimensional vector space. And here we have the product of two generators, and here we have just a scalar unit, one. Uh, Okay, but then when I thinking what to say, not to completely not answer to your question, then I ask Chat GPT for an answer, and this is what I obtained. Very interesting. So he gave me very reasonable answer. I think that could be very well understood, but I will not go through this now. So everybody can stop the video. Can stop the video and read what is written here. Essentially, it's written what I just said in previous slide, but with more explanation. And okay, now I will add the following. So here we have a Clifford number generated over four-dimensional, two-dimensional space with two vector generators, and this can be extended to four generators, and then we get 16 terms because we have, so these are just E1, E2, and so on. Then we have B vectors, C vectors, and four vectors. If you count them, it turns out 16, and so it is 16-dimensional space. It is Clifford space, as I call it, because this vectors Clifford algebra is generalized vector space, and it can be a tangent space to a curved 16-dimensional space.
Okay.
Let me see if I, yeah, okay. Yeah, this was just about a possible way how to explain in simple, but I'm afraid not too simple terms, Clifford space and Clifford algebra. In fact, when I was a student in Catania with Erasmo Recami, uh, I met Professor Valdir Rodriguez, who started to talk me about Clifford algebra. At the beginning, I did not understand much, but after a lot of discussion with him, maybe after several days, 1 week, or even 2 weeks, I suddenly understood, oh, how fantastic is Clifford algebra, useful for physics. Yeah, the concept is difficult because one must understand that these objects, which are Clifford numbers, satisfying the relations of Clifford algebra, are abstract objects like this eye in imaginary is abstract because its square is -1, and so on.
Okay.
Yeah.
So, within the framework of special relativity, what are some of the theoretical challenges associated with tachyons? And
Uh,
also, how would tachyons be affected by time?
One problem with tachyons is causality, as I said.
Mm-hmm.
Uh, this can be resolved in the framework of quantum mechanics and splitting world histories.
Okay.
Yeah. Another problem is the propagation of tachyonic fields in four-dimensional space-time because the initial data cannot be given on a hypersurface T is constant just because of this weird metric signature. But one way to remedy it is to take six-dimensional space. Well, at this point, let me say something more about Clifford algebra. The Clifford algebra is a 16-dimensional vector space, and its signature is 8, 8, which means that it has 8 plus and 8 minus signs. Its subspace is six-dimensional space with signature 3, 3. So it means uh, plus, 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 minus, minus. So three times and three space. And as I said, in such space, we can formulate extended relativity with real subluminal and real superluminal transformations that connect slower than light and faster than light observers and objects. A well-known challenge concerning spaces with indefinite signature uh, is the Cauchy problem, which is well posed only on special hypersurface, namely light surface. So the Cauchy problem is not well posed on on whatever space a three-dimensional space like surface, but it
Okay.
is well posed if this surface is inclined so that it is like it is inclined at 40 degrees with respect to t and x axis. 40 degree because we say that the velocity of light is c equal 1. On such surface, you can give initial data, and then the orthogonal coordinates on that surface is time that we experience. Then you can have well-defined field theory. So in this way, we avoid the problems of tachyons.
Okay.
Yeah, let me see. Uh, yeah. I think how that is clear. Otherwise, please ask me.
I do have one more question over here. Could you define what a hypersurface is?
Yeah. Look, Hyper surface is analogous to the plane. If in three-dimensional space, sub sub subspace is two-dimensional. This is surface, and in three dimensions, uh, hypersurface is three-dimensional. While in four-dimensional space-time, hypersurface is is three-dimensional. Yeah, in three-dimensional space, the hypersurface is two-dimensional. Yeah, yeah, it's difficult because our brain is not thinking in more than three dimensions.
Yeah.
So we must use analogies, and the picture must be analogous. We must suppress additional dimension. So I hope that it's clear if I say that our space-time is a hypersurface in four-dimensional space-time. In fact, it is a three-dimensional space, and orthogonal to this three-dimensional space is another dimension, which is time. And this is the coordinate of the block universe. And our space-time as a hypersurface moves in four dimensions. And so, in fact, we must have then some additional parameter which says what is not our current now. Yeah?
Okay. Yeah. Okay, that was an interesting case. So, do you believe the discovery of tachyons would be a stepping stone towards a more comprehensive TOE, or the theory of everything, or would it require a complete overhaul of our current understanding?
Yeah, let me repeat what I said just before and what I say in my book, Stumbling Blocks Against Unification. So, the discovery of tachyons would be a crucial experiment that would boost the advance of theoretical physics. Above all, it would require the adoption of an Everett-like many words interpretation of quantum mechanics. Next, it would be necessary to place tachyons into an appropriate theoretical framework, which very likely is an extended relativity in in six-dimensional space-time or in 16-dimensional Clifford space. Thus, after 100 years, we would have finally come beyond the theory of relativity. This theory would not be rejected, but only extended, improved, extended. It would be a special case, like Newtonian physics special case of relativity theory. But unfortunately, the physical community is not yet prepared to accept such ideas. Okay, many physicists do, but in general, it's problematic. Yeah.
So, I have one more question here.
Yes, please.
So, because like before the discovery of tachyons, they would need to exist, right? So, assuming tachyons are real or they are possible, at least, how would they be produced?
How would they be?
Produced, or how would a tachyon come into existence?
How would they be? I don't understand. Sorry. Repeat more clearly. The sound
Yeah.
is not.
How would a
No,
tachyon
only the last word I did not understand. How they would be transmitted or
produced?
transmitted,
Produced.
produced. Yeah, this I don't know yet. Yeah, this I don't know. Probably, who knows? Probably they were already produced but not detected by detectors. So maybe better question is how they could eventually be detected. Physicists think that tachyons would be detected if we would detect Cherenkov radiation in vacuum. So they said that in this very famous experiment, which infamous actually, of I don't know 7 years ago, I think it was 11 or what. opera experiment, they, if you know, they announced that neutrinos, detected neutrinos, are faster than light.
Yeah.
Then, in several parallel experiments, they said, but we did not detect any Cherenkov radiation, so that this cannot be tachyons. And later, which for me is a very strange thing, later somehow they found that a cable was not properly plugged. And if you properly plug the cable, then there is no time relay, and then the speed of tachyon is not superluminal but subliminal. But unfortunately, I never saw an explicit repetition of the experiment, not repetition of the analysis. I think that they only made a re-analysis confirming, okay, with the plug properly, the cable properly plugged in, there are no superluminal motion. I would be very happy if somebody confirmed that they ran the experiment with neutrino again with the properly plugged cable and confirmed that the neutrinos are subluminal and not superluminal.
Hmm.
This, for me, how it is explained is somehow unclear. Maybe they did it, maybe they did not. I'm sorry. Okay, but anyway, the detection of tachyons would be would require ingenious experimental methods based on ingenious theoretical insight how this apparatus works and so on. So I have no definite ideas concerning that question. Maybe
Okay.
Rekami wrote a lot of papers on that, uh, but now unfortunately Rekami's work, Erasmo Rekami's work, is is not even mentioned or hardly mentioned in Wikipedia article on tachyons, because today people think about tachyons not in terms of extended relativity, but just in terms of imaginary mass if particle goes faster than light. But this is not in agreement with the principle of relativity, because if there are tachyons, then there must also be observers that move faster than light. But in today's physics, tachyons are just fields with imaginary mass, uh, allowing for negative energies and thus unstable. But we already discussed that this issue of instability due to negative energy must be revised, released, and so on. So there are a lot of things that must be resynced again.
Okay.
Yeah.
So, your book, The Landscape of Theoretical Physics, offers a broad view of the field. How do you see the future of theoretical physics unfolding, considering that many open questions that still remain unanswered?
Yeah, I explained it in the book in the follow-up book, the stumbling blocks against unification. But I think that I already explained in this interview some of my ideas, what
Hmm.
should or what would happen. Yeah. Okay. Yeah.
So, theoretical physics deals with some very abstract concepts, right? So, how do you explain your work to people who do not have a strong background in physics?
I am trying to do my best, but it is very difficult.
Hmm.
I often talk to my wife and daughters when they show interest, and I hope that they can understand something. But now let me tell an interesting story about how explain to layman difficult concept. David Deutsch, I know he's inventor of multiverse. Uh, he interpreted many words theory in much detail, and David Deutsch is also designer of quantum computers based on the concept of multiverse. That is, means the universe of many quantum possibilities. I hope that you heard
Yeah.
about quantum computers. Okay, so Deutsch in a popular article was explaining how multiverse works and quantum computers work. And then in another articles, he explained using different metaphors, a different way. He explained it different, but of course, David Deutsch knew, explained the same theory, but in slightly different ways. Then I was discussing with a professor of philosophy at our University of Ljubljana. He was very skeptical about many words theory, and he wrote he wrote in a book that David, in an article, in a book and also in an article, that David Deutsch is also not clear about his theory of multiverse because he changed his mind and then he said that he's explaining this and now he's explaining it differently. Then when we had lunch with him, I said to him, no, David Deutsch did not change everything. He only changed the way how he tried to explain the ideas to lay person. So it's very difficult. Some persons are very talented, some not. It is difficult. Yeah.
Okay, so this is one of my favorite questions, and one of the questions that my dad has been asking me since I want to pursue a career in theoretical physics. How does theoretical physics help the world and society on a daily basis? And how does it impact and shape the lives of the general public?
Yeah. So how does theoretical physics help the world? Yeah, fundamental discoveries in science usually do not have an immediate impact, but after a certain delay, which can be shorter or longer. At the beginning, there is a lot of dispute and rejection and ridicule. This I described in my book, especially in the introductory section. Um, yeah. Yeah, you can ask something in this relation if you wish. I don't know.
Okay, no, that was it. Because like, my dad was asking how it helps the civilization as a whole progress. Like, there's a random guy walking in the street, right? How
Mhm.
does theoretical physics, like let's say a big discovery happen. Let's say we prove tachyons. So how would that specific person be impacted?
Yeah, with tachyons, the impact would be tremendous because, as I said to you, with tachyons, it would be possible to send signals into to the past or receive signals from the future. What does it mean? Then the world splits. So with tachyons, we will be able somehow to monitor alternative histories because we would receive signal from the future of the person telling me about this. And
Hmm.
so this is science fiction still, yeah. But if there, this would be tremendous
Okay.
impact on society. And of course, we will travel faster than light. We could colonize galaxy. But anyway, even if we do not discover tachyons, robots based on artificial intelligence could colonize because for them it doesn't matter how long they will travel to other stars and so on.
I never thought about it that way. Okay,
Yeah.
so moving on, the education system plays a big role in the mental development of students. So, what advice would you give to teachers or educators who want to encourage students to explore physics and ask questions?
Those who want to encourage must themselves be enthusiastic and competent in their discipline. So the teacher is born. Some are good, some are not. Okay, now I think that I will tell you a story for illustration. I don't know. Maybe you heard about it, maybe not. Anyway, um, look, in 30s, they found that from certain school in Brooklyn, the poor region of New York, there is incredibly uh, unproportional number of of Nobel laureates, I don't know English pronunciation, those who won Nobel Prize from that school. And this was very interesting. And so they made some research. And what they found, that because in 30s there was economic crisis, a number of university professors lost their university jobs. And so they were teaching in that school in Brooklyn. And what happened? From that school, many people came which later won Nobel Prize. Look how important is the teacher is really competent, good, and enthusiastic. What is fascinating that those professors were not deprived, or how to say depressed. They forward their enthusiasm in middle school or high school. Yeah.
Okay, so since we are close to the end of this session, what would be your message to students who are interested in physics or STEM fields?
If they are interested, they do not need a special message. At least that they must be cautious in their interactions with colleagues and teachers, because some of those teachers or colleagues might be hard-nosed and not sympathetic with their ideas and enthusiasm. Look, of course, at the institute I was very enthusiastic and I showed my enthusiasm. So one of professor and scientists on the institute who was very favorably inclined to me once said to me, you must grow up so that nobody notices it. Otherwise, they kill you. This was an advice that was useful for me. Yeah.
So, as a, yeah, go on.
Nevertheless, I was not very cautious, yeah, because everybody at the institute knew what were my interests and so on. So it is not always easy. Yeah, okay.
As a scientist who explores the universe's deepest mysteries, what drives your curiosity and what do you hope the future generations will discover about the universe?
Uh, yeah, as I said in the previous podcast, I was embedded into a very stimulating environment of my family. And I early decided to become physicist. Fortunately, I met some very inspiring physicists and had a privilege to work with them. The insight that I obtained from Erasmo Recami, Asim Barud from Boulder in Colorado, and Valdir Rodriguez from Campinas in Brazil was tremendously important for my development as a physicist. I hope that the future generations will discover that objects can move in scale so that the spectral lines emitted from such object would be shifted, which would explain some of the problems in current cosmology. Because if object move in scale, then the frequency of the emit light is moved as well. So people usually assume that the red shifts or blue shifts are caused by motion, even by gravitational field. But
Yeah.
this would be another source of red or blue shift. I think that this could resolve certain. If somebody is interested, one can look into my bibliography uh, and we will see. I also hope that they will find a way of traveling faster than light by suitably generating relativity. And who knows, perhaps we will also become a web traveling civilization as envisaged in the other side of time.
I mean, that is probably too ambitious for a civilization since
Yeah,
we lack water.
this is maybe, who knows?
Yeah.
Traveling to moon was something completely crazy 100 years ago. But Gilbert already envisaged it. Sometimes science writers are ahead of scientists.
So that is it for this session, sir. Thank you for joining. Thank you for your time. It was again great interacting with you. And I think I will go through your books again now that I have a clearer understanding of the whole concept. And I will ignore the mathematics because it's a little too complex for me. Uh, so thank you again.